All right, so I'm going to go over section problem 4E and talk a little bit about like best case versus worst case, stuff like that for doing this code modeling stuff, which is basically taking code that might look like this and constructing a big O bound for this like code model. So what I did here was I just copied over exactly what was on the section handout from 4E, and we want to analyze this code, and the prompt asked us to find a worst case runtime of the following code and to give a type big O bound for our model. So if this is our code, we want to give it type big O bound. So the first thing that I want to talk about is we talk about this find a worst case runtime here. And I just wanted to quickly touch on what we mean by worst case runtime. So kind of over here, like when we're thinking about like the different cases that our method has, like we kind of want to know like, okay, given this code here, how many different cases does this method have? So if we go kind of over here, we kind of saw in lecture a couple of examples, one where we might have had a best case and a worst case, or a bunch of different cases, Zach showed, and we had another method where there was like no best, or the best and the worst case were kind of the same case. Like there were no cases, there was just like one case here. So the things to be thinking about when you're thinking about like, okay, if I want the worst case, the first thing that you should think about is like, can I change anything about the problem except for the variable that you're analyzing? So in this case, when we're looking at this, it would kind of be like the variable that we're analyzing is n, because we want to give a runtime model for n. So we should be thinking about like, can you change anything about the problem except for n, basically in this case. The reason that we can't like choose n to be a certain value is that we are looking to construct a model for the runtime of this function as n approaches infinity. So like we can't ever constrain n to be like one value, or like constrain n to, for example, be only even or only odd, because we want our like the model that we come up with to work for like every single n possible, right? For all n, whatever model we come up with better work is like the idea. So you can never like constrain that n variable to be anything, basically. So you can only constrain other stuff about the problem. So here in this case, right, if we look at the problem and we say, can I change anything about the problem except for the variable I'm analyzing? If the answer is no, there's only going to be one case for our method. And the best case and the worst case are going to be the exact same. If you can change things about the problem except for that variable, an example that we showed was like, maybe if we're analyzing a method that takes in, like maybe if n is the length of a list, for example, like we can't actually like constrain the length of the list to be anything, but we could change the like ordering of the contents of the list. So I think we showed an example where like if you're finding a value in the list, if the value is at the very beginning, you might get a much different runtime than if the value is at the very end. In that case, n was still the length of the list, but like we didn't have to constrain n to like change the ordering of this list. And I'll get into a concrete example about this, so it's okay if it's still like not making 100% sense. But then basically like the other thing you kind of want to be thinking about that might help is to think about like, if I drew a graph where like the y-axis was like the runtime and the x-axis was like n, could you draw like multiple separate runtime functions for different cases, basically here? So that was kind of a mouthful. Let's go back to the problem and kind of think about this. So in this problem, we kind of see, there's not a whole lot going on. Basically, we just have an if check. If n mod 2 is 0, we do sort of like this n to the fourth operation. Otherwise, we do like an n cubed operation. So like a common thing to think about this is to think about like, okay, well, the problem is asking for worst case runtime. So it seems like the worst case would be like if we went into this first if check, right? Like that's the worst case. It looks like that goes like n to the fourth time, and this one goes like n to the n cubed times. So like I'm just going to say that this is the worst case runtime, is that it goes into this first if check. But remember, we can't actually constrain n to be anything, because that's what we're analyzing, right? We want to come up with a function that works for any n, right? For an arbitrary n that's not constrained to anything. So I can't just say like, oh yeah, my model kind of only works for n's that are even, or my model only works for n's that are less than 1,000. We have to really be thinking about as this thing goes to infinity. The other thing too is like if we went back to this point, can I draw multiple separate runtime functions for the different cases? And what I mean by that is like if you were given a graph where let's say you have the number of steps or like the runtime as the y-axis, you have n as the x-axis, and kind of we want to know what happens as we increase n to infinity. We can kind of start drawing things and say like, okay, well if n is 0, well, let's just start with 1 because I just drew this graph kind of wrong. If n is 1, well, if we went back to, oops, excuse me, sorry, my background is really messy. If n is 1, okay, that's going to go like n cubed times, so maybe we do like, 1 operation or something like that. And then if we went to like n is 2, okay, now we get like n to the 4th, so 2 to the 4th, that's 16. So we can go back here and we can say like, okay, maybe the 2, we would be like up, here somewhere, like 16. Then we go to 3, and 3 cubed is 27. Yeah, math right on the spot, right? So 3 cubed is like 27, so we kind of maybe are somewhere up here. Et cetera, right? I'm just kind of like drawing out these points, and then you could imagine that you connect these points with like a line or something to get that runtime function. But like the main intuition here is that like when n is 1, like if I said like, okay, for n is 1, like how many different cases do I have here? Well, if I looked at the function again, if n is exactly 1, there's not any cases, right? There's only one thing that can happen for every single n, right? So if n is 2, there's only one thing that can happen. I can't get like different runtimes when n is 2 because that's just how the problem was defined, right? So if I kept drawing this out, you'd see that like for every n, there is one single point, which would kind of like make us think that there's only one function that we can draw for this method, right? There's only one function that we can draw. We can't draw multiple different functions. So hopefully that kind of makes sense. But I kind of wanted to dive into maybe just like a quick example. This wasn't on the section handout, but just like something to keep in mind. Maybe we can think about like, okay, well, what is an example where we have a best and a worst case, right? Because if this isn't one, then like, what is one? So here's a contrived kind of hypothetical problem. And we want to do the same thing here. Oh, actually, sorry. Before we get into this, I just kind of wanted to finish this up right here. So if we were looking for the worst case runtime of this code model, well, like, if we kind of kept graphing these points as n goes to infinity, you would see that like basically whenever n is even, we get like an n to the 4th runtime, and whenever n is odd, we're going to get an n cubed runtime. So the tightest big O is going to be O of n to the 4th, right? Because I will have those n to the 4th. Every time n is even, I'm going to get an n to the 4th runtime, so I can't upper bound it by anything lower than that. The tightest big omega is going to be O of n to the 3rd, actually, because I can't lower bound it by anything greater than n to the 3rd, right? Because no matter what, every single odd n is going to give me that n to the 3rd runtime, right? In this case, we only asked for a tight big O bound for the model. So the correct answer would be this. So if you just put O of n to the 4th, that's the correct answer for this. But just something to kind of keep in mind, just like as a kind of a review, if we asked for a big theta of this function, the answer would be that there is none. And that's because the tightest big O and the tightest big omega are different classes. So there's no big theta bound that kind of describes this function. So yeah, if we asked, so this is like for the worst case. For the worst case, we have all three of these things. And the same thing for the best case, right? Because we kind of said for the best case, again, there's not like, the best case and the worst case are the same here, right? For the best case, I still have that same behavior where every single odd index takes n to the 4th runtime. Every single even index takes n cubed runtime. So sorry, let me make this omega. So, you can see we have, in the worst case, we have a big O, a big omega, and no big theta. For the best case, we have a big O, a big omega, and no big theta. So just like a quick review, big O and big omega don't necessarily mean best case and worst case. You have a big O and a big omega for the worst case, and a big O and a big omega for the best case. So the answer to this is O of n to the fourth, because all that we asked for was a tight big O bound for our model. So that's the answer to this section problem. Okay, moving on to just like a quick example. If you're only here to look at the section solutions, then that's kind of it. But this is another hypothetical problem where we actually do have a separate best case and worst case, and we're going to go through why that is. So in this case, what I do is I say int x is just math.random. This returns a number in the range 0 to 1. I forget exactly which is inclusive and exclusive. It's not super important, but basically you just have to know it returns a number between 0 and 1. And I'm saying, okay, if x is less than 0.01, so this is about like a 1% chance, I'm going to go into this method, and this runs n squared times, as you see. And it just prints out, one statement, n squared times. Otherwise, it goes down here, and it just does one single operation. So I went back to this, like, how can I tell type of thing. I would ask, like, okay, so the variable that I'm analyzing is n, right? So I can't really, like, force n to be anything. Like, I can't say, like, constrain n to be, like, less than a number or n to be even or odd. I can't do that here. But can I change anything about this problem except for that variable? Well, what I could do is I could say, like, okay, well, maybe I could change, like, the randomness here, right? Like, I could say, like, okay, well, math.random, let's just say it always returns 0 or something like that. Like, I'm always going to go into this case. In this case, like, I'm not actually constraining n to be anything, right? I'm changing some other aspect of the problem, which is, like, this randomness or the ordering of a list or another variable, right? I'm changing something else. So in this case, we're actually going to have a separate best case and worst case. Because we can change that randomness. And the other thing, too, is to think about, like, can I draw multiple separate runtime functions for the different cases? The answer is kind of yes, too. So if we went down here, let's think about the graph for this type of problem here. So if I asked, okay, when n is, let's just start with 1 again, because that's easy. Actually, let's start with 2, because this is where it kind of starts getting interesting. If I said, okay, when n is 2, how many different points can I have on my graph? Well, okay, I mean, I can either have, if n is equal to 2, right, n is constrained to, n is just 2, can I have multiple different points on the graph? The answer is yes, right, because I'll have maybe one point where, I have one case, basically, that x is less than 0.01. So I'd have kind of like one point where, we go up to 4. And this is like this right here, right? This is like if x is less than 0.01, we have a point there. And we'll have another point if x is not less than 0.01, we're just going to do one operation. So I'll go over here and I'll say like there. So this is like if x is greater than or equal to 0.01. And this is kind of the case for any n. For every single n, we're going to have just 2 different points, right? We're going to have one point on our graph if x is less than 0.01, and we're going to have one point if x is greater than or equal to 0.01. And so since for any given n, you can have 2 different points, that kind of would clue us into the fact that there are different functions here. Like there are separate runtime functions depending on this randomness, right? Where I have one where we kind of are growing at n squared, and one where we're not growing at n squared. Because for any given n, I can have multiple different runtime functions. And this is, not the same as up here, where if I said n is 1, there's only one thing that can happen if n is 1, right? I can't have multiple things happen if n is 1. Versus down here, if n is 1, there's multiple things that could happen, right? I could either go into this case or this case. So just some food for thought. So in this case, like the best case and the worst case are actually different. So if I was talking about the worst case in this example, it would be like an n squared runtime, because we're going to assume that it kind of always goes into here. Like we can control that randomness and say the randomness is always going to make us go into this if check. And then the best case would just be O of 1, basically. So we could say like tight O for worst case is O of n squared. And the tight O for the best case, for the best case is O of 1. Right, because in the best case, I'm going to assume that it never goes into this function, right? if I looked at my graph, the best case runtime is going to be sort of like down here, where for every value, we have one single point. So if I kind of connected all those lines, you'd get just like a flat constant runtime. So that's just some stuff about best case versus worst case. It's, yeah, a little confusing. Definitely check out the other video on problem 4 in this playlist if you want another kind of perspective on best case, worst case. Yeah, and feel free to like post on Piazza or yeah, reach out if you have any questions about this stuff. Yeah, cool. Thanks.